Tonight, Chris Steffen is going to talk to us about his Raspberry Pi implementation in the lab to help probably become far more efficient than we were previously. So Chris is currently an advisory engineer at IBM. He joined IBM in 2013 and has worked in the circuit design area on I/O firmware and lab bring-up. He holds a bachelor's degree in electrical engineering from South Dakota State University. And his current responsibilities include high-speed SerDes microcode, which maybe is what we'll talk about a little bit tonight, I/O lab bring-up, and is part of the RX logic design team. Thanks, Chris.
Hello, can you hear me? Yeah. All right. Well, thank you. I want to say thanks everybody for coming tonight. I was asked to give a little presentation about what I do at IBM, a little project that I've been working on, specifically the Raspberry Pi high-speed SerDes characterization platform. A little bit about me. So I got my bachelor's degree in EE at South Dakota State University, and shortly after that, I came on to IBM, and I've been working there ever since here in Rochester. And I feel blessed because as I came on, I've got to do several different projects that have given me the freedom to work on stuff that I really enjoy to do. When I first came on, I started in some analog circuit design, mainly PLLs. That really gave me the background of how bleeding edge hardware works here at IBM and different techniques that we do from the hardware standpoint. And then I also picked up some I/O firmware, and I am now the I/O firmware lead, and I own the firmware for P and Z that do all the initialization and link training. And then I also picked up I/O lab bring up, and this includes wafer testing, VBU, which is virtual bring up, and then also system lab bring up. And the system lab bring up was really helpful because now you got to see the point of view instead of from being heads down working on hardware, you got to see how the entire system works, how our links actually interact and talk to different interfaces and memory and GPUs and accelerators. So today I'll go through a little bit of the background about what a SerDes designer looks for and what we strive for. And then we'll get into some solutions of what we've had in the lab previously and where we're at now with the Raspberry Pi. And then after that, we'll dig into some results and how we can now visualize different things that we weren't able to before, and some issues that we've been able to correct. On the right hand of this slide, you can see this was actually taken in our lab here in Rochester. This was a particularly lossy channel, and this is what we look at day in and day out. This one is particularly bad. I don't know if we would be able to recover this data, but this is kind of what we dig into. And if you look hard, you can see that the ones and the zeros are not crossing a 0 volt threshold. So this makes it particularly difficult to recover the data. So a SerDes ideal outcome. This upper image here is a small data I, and this is what we would normally see out of a channel. And the data I, when I say a data I, I'm really making reference to the inner black zone where you can easily, stably represent a 1 or a 0 in between the transitions. And then this bottom image is what all SerDes designers strive for, is a wide open eye where you have plenty of vertical amplitude, and then you also have plenty of horizontal margin there. With little jitter, this is very good because then you'd have a low bit error rate. So in that previous slide, I showed you a little bit about how we have a small data I, And this is due to when we have long channels and we have multiple connections. So if you look in this upper right-hand image, you can see that we have an IBM processor and then a module, LGA connector, and then the signal would go through a motherboard and then up into a different device. And that device could be a GPU, it could be a memory, accelerator, really anything. But there's plenty of points for us to lose signal amplitude and loss of the signal, really. And that's why we get a closed eye when we transmit a signal through all those different areas. So link training is the process of opening that data eye and recovering the data signal after it's been attenuated through this lossy channel. And these are a few of the steps that we do in this link training. And we do latch offset cancellation. We get latch offset in our circuits just due to the process variation. And we have a way to cancel that out. There's VGA, variable gain amplifier. This really helps with our low frequency signals. CTLE, continuous time linear equalizer. That's a mouthful. This helps with our high frequency signals. Data centering, FFE, which is feed-forward equalization. We can do this on the transmitter to help with the data. DFE, decision feedback equalization. This is a step where we can look at the previous bits and see how those influence our current bit. And then from there, we can move where our sample point is. And that's intersymbol interference, so we can reduce that. And then there's FEC, which is forward error correction, which is another idea that's been around for a little while, where you can correct errors in the post-processing steps. There's more than that, but those are just a few. And here I'd like to show you just a little animation. So what you saw right away was the eye was completely closed, but as we apply these different steps, we can actually open up the eye where we can get a actual data eye there and sample some steady points. And then if you look closely, there's also a pink curve coming down. And this is the error rate. So as long as we're sampling in between, we want to be sampling at the center of that eye, and then we have a very low error rate, and we have a very high chance of sampling the data correctly. So we are given a challenge to verify our link training algorithms. And all those algorithms that I stated just before, those are very complicated and very difficult to do in hardware state machines. So the challenge was to try to verify these before we harden these into our processors. And so our idea, we thought we might be able to do this here in Rochester on one of our wafer probers. And in this picture is a wafer prober that we have down in Building 40. And this is just a piece of granite in the chamber. And then there's you stick a 12-inch wafer on top of that, and then we have probes that can land on top of that wafer, and we can create a test site to land on. And then we have different signals coming out. We can have low-speed and high-speed signals, to where we can send signals in and send high-speed data out and characterize that data. And what's nice about this is it's all temperature controlled. We can control the voltage. So we can really control everything and every aspect and test different corners as we go throughout this test characterization plan. So our proposed solution to characterize these algorithms is to put a TX and RX on the same test site. And here's an image of a test site that we would create, and we would put this on a wafer, and we would be able to land our probes and test this. So if you look on the upper right-hand side, you can see we have a TX and RX, TX on the top and the RX on the right, with some logic in between. And this was kind of really exciting because this was one of the first times we've been able to put a transmitter and a receiver on the same pad gauge. Previously, we've had these separate. So this was really something new. And the idea was you'd be able to transmit data and loop it back to the receiver and then take those sample data points and process that and update new settings. And then we could do all of our feedback loops in software. So in the red, you can see some of those pads would go to a microcontroller. So we would take the received data to the microcontroller, process that, number crunch it, and then send back in the learn settings. And by doing several million iterations of this, we would be able to train the entire link. And so another requirement we had for this was to train the link in less than an hour. This wasn't a hard requirement. This was just so that we could iterate on the process and in an efficient manner. And this meant that we must have a fast feedback loop, that feedback loop where we're receiving sample data and then updating learn settings. And that, at first we thought this was going to be very challenging to do. So our previous solutions was a digital analyzer. This is a roughly 10K, and it's not, I don't have anything pictured here, but the tough part about this was the round trip latency of updating that learn settings and analyzing those was greater than a second. So when you're doing a million iterations, this is just not feasible in a timely manner. So then we moved on to an Arduino Uno, and this was really just a proof of concept to make sure that a microcontroller would work for us. And this Arduino Uno, we wrote some C++ code that would run on that, and really it was just to send and receive signals back and forth to the pad cage and level shift that data, which was connected then to a PC via USB. And we would send data over that USB via serial. And the round trip latency from the PC all the way to the pad cage and back was about 7 milliseconds. So this was a huge advantage over the digital analyzer. And then we developed some C# code for a user interface on the PC side. And this allowed us to easily send in settings and run our link training algorithms. So then we iterated on that, and then we finally got to using a Teensy. And this is a microcontroller that you can buy from Amazon, online, anywhere really. And in the upper right-hand side, you can see a picture with the microcontroller and then a daughter card that we designed. We designed that daughter card in-house and then sent that off and got it built. And the daughter card really only does level shifts all the signals back and forth because the pad cage is running at a much lower voltage than the microcontrollers are. And this was a huge step up from the Arduino Uno because now this is running at nearly 100 megahertz, whereas the Uno was running at 16 megahertz. And it was just a faster ARM core. The round trip latency was now under 3 milliseconds. And we used the same techniques where on the microcontroller we were running C++ code, and then we had the same C# user interface. But both these microcontroller platforms had the same problem. You had dual code maintenance, so you had C++ code on the microcontroller, and then you had C# code on the PC that you had to maintain together in unison. So if you changed one, then you could be out of sync. And then you also had PC device drivers. And this became difficult when we had multiple people in the lab and we were using multiple laptops. The device drivers would get out of sync, and then we would have to update and keep version control everything. So we needed something a little different. And that's when we landed on this Raspberry Pi solution. This has an even more powerful microcontroller in there. Really, it's a processor at this point. It's a quad-core ARM running at 1.2 gigahertz. And then we created a custom daughter card. And we designed this internally. And the daughter card can be seen on the right in purple. And the Raspberry Pi is the green card there. And that can also be bought off Amazon, just like any of the other solutions. And in this case, our daughter card you did the level translating again, and then we had a small ADC on there for different experiments. What was kind of neat about the Raspberry Pi now is now that we are able to have a full Linux OS on there. So now we can store files on there, we can store all of our code on there, and it completely eliminated a PC out of the picture. So this was our PC. And then we were able to develop C++ and Python on top of that to run all of our scripts and all of our processing on the actual Raspberry Pi. Another advantage was the network connectivity. So as you can see there's an Ethernet port. So we can connect this straight up to the network, and then we can remote access in from our office, from home, from really anywhere, and we can check in on scripts, kick off different scripts, and check the different status of the lab. And now the round-trip latency, because we were able to do all this, the round-trip latency really was much faster, much less than a millisecond now. And another part of this was we changed the interface between the microcontroller and the pad gauge to a SPI interface. And this gave us a 16x performance increase. And SPI is just a industry standard interface. So then we were using the actual SPI engine on the Raspberry Pi. So the several advantages of this was faster training times since we had better round-trip latency, remote access. We were able to run Linux, and now we have a single code source, which was great. And now when we have multiple of these Raspberry Pis throughout the lab, all of our code is stored on GitHub. So we can really, whenever we make a change, we can push it up to GitHub and then pull it down onto all these other Raspberry Pis so we can stay in sync everywhere. And then the other part of this I didn't mention just yet is the GPIB access. We have so the Raspberry Pi has USB ports, so we have a USB to GPIB converter, and GPIB is a general purpose interface bus, and that is a way to control all of our oscilloscopes, all of our power supplies, pattern generators, everything. Every lab equipment has GPIB. So now not only can we control the pad cage and do all of our processing on the pad cage, but now we can control all of our lab equipments. So now we can vary voltage, we can check our oscilloscope and check how healthy our signals are and check frequency and different things like that that we were never able to do before. So to take this, to get a bigger picture of what our lab experiment actually looks like now, in the center you can see this is our pad cage. So this is a little different than what I showed earlier in that there's a PLL now in the bottom. So we can drive that PLL with a reference clock from a signal generator, and then we can, down the bottom side, we have some high-speed probes where we can probe that and check how healthy our PLL is. And then that PLL is just creating a higher speed clock for our transmitter and our receivers. And on the top side, you see a transmitter and a receiver, and that is looped back around with SMA cables. And another note on the SMA cables is we can use a channel board in between those SMA cables with a lossy material to mimic what a system channel would look like. And this is very important as we can now create channels that look exactly like our systems or even worse to know that we have margin. And this is all controlled by the Raspberry Pi on the lower right via the SPI interface. And the Raspberry Pi is really the grunt. It does all the grunt work and all the processing and controls everything on this entire setup. And then on the bottom you can see that we have this GPIB connection to control our signal generator, our oscilloscope, and then the power supply that's not pictured in this image. So then we're getting into a little bit of the results. Then we are able to characterize our transmitters. And I can't go into too much details about speeds and feeds about all this, but I can give out a little bit that the pictures on the right-hand side here, what we are able to do is vary the amplitude of this clock waveform on both the a differential P and N leg. And this was nice because when we actually did this is we were able to set up the scope via the Raspberry Pi, change all these settings and set traces and different things over GPIB and send these settings into the pad cage, and then save the waveforms and pull it back onto the Raspberry Pi. So we were able to take all these screenshots without ever even being down in the lab. And then the picture on the left here is just another data eye. And we were able to do the same thing here, where we are able to set up the data eye. I think in this image, we didn't do this all on the Raspberry Pi, but we could have. And that's kind of what shows the strength of this remote access controller that can control your entire lab network. So here's another one of those link training algorithms. This is on the receiver side. This is latch offset cancellation. So ideally, you would have your latch switch at 0 volts, sampling latch, but that doesn't happen. As the process varies throughout the entire chip, from different wafers, from different lots, your latch offset is random. So on the left-hand side of this image, you can see that we have 4 latches switching at different points. And that's what those different colors are. And what we're showing here is just the switch points of the latch. So anything on the 0 end is sampling a 0, and then as I sweep the latch, I can get it to sample a 1. And ideally, we'd want this to switch at exactly 0, that red ideal point. So we run this latch offset cancellation, and then we can get to this right-hand side of the picture where everything is switching right at 0. And this was cool because we were never able to visualize this before. We were able to, we understood what latch offset did. We understood it's been around for a while, but we were never able to show exactly how far and what all these latches, how we can calibrate them and see this visually. And this really took this lab platform to the next level. Because now we can make these graphs and we can do the same experiment in simulation, and we can compare results and get model to hardware correlation, and really compare and contrast to see where our circuits are differing and what some problems could be. Here's yet another algorithm that we are able to visualize that we weren't able to before. This chart is really split up into 2 parts. There's VGA calibration on the top and then CTLE on the bottom. And VGA calibration is variable gain amplification. And that really helps our low frequencies to our DC signals. And the upper left-hand image, you can see this is a scope mode. In this mode, we are able to send a repeating pattern to the receiver and sync up the receiver so we could sample that at the same point every time. And with that, we are able to test different settings of our VGA, and see how it reacted. And in this case, the blue is with no gain, the green is calibrated, and then the red is max gain. And we are able to see how different frequencies and different signals were able to react to those different settings. And the green calibrated signal is what our algorithms picked. And this was a way that we could verify that these algorithms are working correctly and how we intended them to work. And then the right side is after we applied that VGA gain calibration, that's what our data eye looked like. So we had a data eye. It wasn't necessarily as big as we would like, but nonetheless, it was there. So now if we go to our CTLE calibration, it's set up the same where the blue is with no peaking, and then the green lines are calibrated, and the red is with max peaking. And you can see that CTLE calibration really helps our high frequency signaling. And on the right-hand side of the picture now, after we run our calibration, our eye is much more wide open. It really helps with the amplitude and the horizontal margining. And now RX decision feedback equalization, DFE. This one was particularly interesting because DFE we've always struggled with DFE. DFE is a really complicated algorithm that is very difficult to implement in hardware. And so we really wanted a way to test this and validate that our algorithms are working correctly and working as intended. And DFE, so what DFE does is it looks at your previous bits because there's inter-symbol interference. So your previous bits have influence on your current bit. So if you can get a feedback from whether your previous bit was a 1 or a 0, you can change the amplitude in which you are sampling your current bit at. And that's H1. And then you can go to look at the 2 previous bits or the 3 previous bits. And you can keep going and add that sum of feedback in and change your amplitude which you're sampling at. And so in this case, the inner blue is with no DFE. And then the red is when we apply H1. And that gave us a big gain right away, specifically in amplitude. And we expect that because we are adjusting the amplitude. So we should get some amplitude gain there. And then the rest of the iterations are H2 through H12. And as we apply those, we get diminishing returns because further out, 12 bits out, you don't expect that to have much of an influence on your current bit. And this was cool because we've never been able to look at this visually. In this case, we can actually inspect and realize that our algorithms are actually working the way we intend them to work. And now to a RX phase rotator issue. So this is really split up into a chart on the bottom and the top, and I'll start with the top. Each cell is an error count, and so an error count of 0 is good. That means you got no errors, and this goes all the way up to 65,000. So the red is bad and the green is good, and you can see that we have this nice big wide open data eye in the center. But if you look closely, you'll see a column of errors right in the middle of our data eye. And this really confused us right away. We weren't sure what we were looking at. We actually thought it was something in the lab. We didn't think that this was real. And then we started to notice that exactly 16 steps away, there was this same column of errors. And that was really intriguing. That was our first clue that we were onto something here. So we then proceeded to shift the data and clock skew. We really delayed the data from the clock, and we could move this column of errors throughout our data eye. And that kind of really pointed us into a single circuit, and we were able to root cause this circuit and find the issue. And the issue really was that certain phase rotator positions, we were getting too much jitter and missing clock cycles. And this particular issue, it would have been very difficult to train the link with this error in here. There would be several steps where we would fail. And the other thing about this is, even if we did train the link, this would happen, this would show up. It would be very difficult to debug in a real system. The Raspberry Pi platform has really allowed us to collect this data faster and been able to give us extra hooks into the receiver and the transmitter that we wouldn't be able to look at in a real system. So in conclusion, processing near the hardware was a huge step. As we got further away from a PC and brought a Raspberry Pi with all the processing power as close as we can to the actual pad cage, we are able to really collect more data and better data. And that was a big key for us. And as we are going along, we've been able to develop new training algorithms. Not only verify our old algorithms, but now since we have everything in software and it's not hardened in hardware, we can develop new algorithms and tweak our old algorithms and really even think of new ideas that we've never been able to test before. And then lastly, this has been able to give us stability and confidence in our designs, and that we've been moving on to the right direction, and our designs are moving forward. So overall, the Raspberry Pi has really brought us to another level in characterizing these data platforms, and collecting data and giving more confidence in our designs. I want to just thank everybody for coming tonight, and does anybody have any questions?
You mentioned that there was, in your DFE test, there was diminishing return as you added terms to the equation, and I assume that was with relatively clean link. Have you tried it with a link that has lots of far end crosstalk, or a big impedance discontinuity gives you a nasty reflection towards the beginning of the next bit?
Yeah, we have. We've influenced the link by adding different reflections at different points. And what we found out is even at these high data rates, you get such an attenuation in your signal, and the signal's so lossy that even those reflections that are bouncing back are attenuated so much. And so even on those further out taps, sometimes at a certain point it's not worth it. And then you get quantization errors with the digital logic too.
So given modern low loss materials, what would you think would be a comfortable DFE tap maximum you look to implement in new designs?
Yeah. I think it would be tough to go past even 6 to 10.
Right.
Yeah, it'd be tough to get much past that.
Like for Megtron 6 or Tachyon, really good materials.
Yeah. I don't think you would get much return from going past 6.
Can you comment on how much effort you put into building this platform and then supporting the platform compared to, just for frame of reference, how much effort you save in doing this manually?
Yeah, it's hard to quantize that. I would say that everything's come so much easier when you're working on a complete operating system than working on a microcontroller with dual code maintenance, or working on a digital analyzer where you're kind of handcuffed to a certain coding standard from Keysight or some other any other platform out there. And what's really allowed us to gain a lot of time back is the remote access, where we can work on it from the lab or from our offices and kick off different tests without having to be down in the lab. I'm not sure if that answered your questions. It's tough to quantify. Yes.
So all of the work so far has been on NRZ systems. You can adapt the same kind of a thing for PAM4 in the future?
Yeah, we don't have any. Yeah, we definitely could. We don't have any plans of doing that yet, but we could easily adapt that to PAM4 since we would have our receiver and driver. It's really independent of what receiver and driver architecture you use.
Have
Yes.
you been able to leverage these into any patents, maybe process patents?
I haven't yet. Since that, most of, the microcontroller and the Raspberry Pi community and all that part of it is pretty established at this point. And that's one of the reasons we picked the Raspberry Pi, is because the community is so large. But I haven't yet, no.
Are you aware of this being used? I guess the how do I want to ask that? Outside of IBM, by any chance? I mean, did you bring some of your lab work from school into this, or where did the motivation come from?
Yeah, so yeah, in school we did a lot with microcontrollers, and that's kind of where everything started from, where you could see, initially when I came down to the lab, you could initially see that there was some innovation to be had right there right away. And that was just due to how difficult it was to scan in different settings and different things, where we can toggle signals now so easily with different microcontrollers. Internally to IBM, this has been picked up by other teams other than ours. Other teams are starting to see this and gain traction, and it's really becoming a good thing.
Any other questions? Anything else? All right, well, thanks, Chris.